Okay, so here we have the magnetic component of a polarized wave of light is given by this. Parallel to which axis is the light polarized? All right, so we know that the B field must be traveling along the x-axis. And how do I know that? Well, we've got a subscript x here. So the subscript x gives this away. Okay. We also know that the wave propagates in the y direction. How do I know that? Because we have our y factor here. This is our wave number, and this is the direction of propagation. Therefore, using our right-hand rule, or we don't even need to use the right-hand rule. We just know that E must be perpendicular to B, and they both must be perpendicular to the direction of travel or propagation. So since the B field is in X, the wave is propagating the Y, that must mean the E field is parallel to the Z axis. So it should be parallel to the Z axis. Okay. That's part A. Part B. A beam of initially unpolarized light is sent through two polarizing sheets. One is placed on top of the other. What must be the angle between the polarizing directions of the sheets if the intensity of the transmitted light is to be 1/3 of the incident intensity? Okay, I'm going to do this down here. So we know that it is initially unpolarized. Therefore, I1 equals 1/2 I0. So if we were to draw this, so we have two sheets. We've got light coming in this way. So this is at some sort of angle theta. We don't know what it is. We can just say that this is polarized vertically. It doesn't really matter. They just need to be at some relative angle to each other, theta. And this is unpolarized. So if this is I0, this is going to be I1. This is going to be I2. Okay. So we know that I1 has got to be 1/2 I0. Okay, I2 has to equal I1 cos squared theta. Now, we also know that we were told in the question, we want the intensity of the transmitted light to be 1/3 of the incident intensity. So I2 divided by I0 has to equal 1/3. And that's because we were told that the transmitted light, which is I2, has to be 1/3 of the initial. Okay. So let's rearrange this equation to put I1 into here. So we can have I2 equals 1/2 I0 cos squared theta. Therefore, we can say I2 divided by I0 has to equal 1/3 as per what the question told us. It's going to equal 1/2 cos squared theta. So if I continue this up here, we end up with 2/3 equals cos squared theta. Okay, so then what we're going to end up doing is we're going to say theta is going to be the inverse cos of the square root of 2/3. Okay, so if we actually do that, I get roughly 35.26 degrees. Or 35.3 degrees. Cool. So that's the answer to part B. Part C. When red light in vacuum is incident at the Brewster angle on a certain glass slab, the angle of refraction is 32 degrees. What are the index of refraction of the glass and the Brewster angle? Okay, so we know, let's actually just draw this. So we've got incident light coming in. This here is our Brewster angle. We've got some refracted angle here. This is our reflected angle. Now remember, this here has to equal 90 degrees. This, according to the law of reflection, has to be the Brewster angle. Therefore, as per what we found in the lectures, the Brewster angle plus the refracted angle must equal 90 degrees. Okay, so we were told that the angle of refraction is 32, so we can actually work out the Brewster angle straight up. It's going to be 90 minus 32 degrees, which is going to equal 58 degrees. Okay, so it's in a vacuum, therefore N1 equals 1. So when we work out our, using our Brewster angle equation, it's going to be N2 divided by N1. Now N1 is 1, therefore tan theta of the Brewster angle equals N2. Therefore, N2 is going to equal tan of 58 degrees. Then when we do that, we get basically exactly 1.600. So that is the refractive index of glass, and that's how we do this question.